These wires came from the same reel of steel and have the same area. One is twice as long. Within the proportional region, the same force makes the longer wire extend twice as far. Is the shorter wire's steel stiffer? No, the dimension changed, the material didn't. Last lesson's spring constant described the whole object, but to compare materials, we need to remove the geometry. Tensile stress is force divided by cross-sectional area. It measures how concentrated the pull is. It's measured in pascals, which are just newtons per square metre. Our test wire is 2.00 metres long. Its area is 0.20 square millimetres, or 2.0 times 10 to the minus 7 square metres. Under a load of 20 newtons, its stress is 1.0 times 10 to the 8 pascals. Tensile strain is extension divided by original length, the fractional change in length. If this wire extends by 1.00 millimeters, its strain is 0.001 divided by 2.00, giving 5.0 times 10 to the minus 4. Strain doesn't have a unit because it is one length divided by another length, so the meters cancel. This value is also 0.050%. Convert a percentage back to a decimal before using it in an equation. So within the proportional region, the Young modulus is stress divided by strain. Here 1.0 times 10 to the 8 divided by 5.0 times 10 to the minus 4 gives 2.0 times 10 to the 11 pascals, the usual scale for steel. A large Young modulus means that a large stress produces only a small strain, so the material is stiff. But that does not necessarily mean that it is strong. Substitution gives a Young modulus equals FL₀ divided by A delta L. The AQA datasheet gives the component equations, so rebuild this form rather than trying to memorise a fourth equation. Plot stress vertically against strain horizontally. The initial straight line gradient is the Young's modulus. Use a large triangle and include any axis multipliers. Once the graph curves, however, the ratio is no longer constant. A force extension gradient gives the spring constant, not the Young modulus. Beyond the straight region, the curve shows how the material deforms and eventually fails. A ductile material yields and then undergoes a large plastic strain before fracture. A brittle material just fractures with little or no plastic region. The breaking stress is the greatest tensile stress that the specimen withstands before fracture. It's not the same as stiffness. Rubber's shallow curve steepens as its molecular chains straighten. It can return to its original length even though the graph is not straight. So elastic is not the same thing as Hookean. The area between its loading and unloading curves is the energy dissipated per unit volume. This is mainly as heating. Now let's clamp a long thin metal wire and use a small preload to make it taut. Record the test length and zero marker position. Measure the diameter with a micrometer at several positions and in perpendicular directions. Find the mean and then calculate the area using pi d squared divided by 4. Add masses in steps over a low friction pulley. Relative to the preload, delta F equals delta mg. Measure delta L from the 0 after the wire settles. Keep everything within the proportional region and then unload to check that you've got elastic recovery. Use those changes to calculate stress and strain and then plot the graph. Its straight line gradient is the Young modulus. A long thin wire produces a larger, more precisely measurable extension because the area is proportional to the diameter squared, but its percentage uncertainty is about twice that in the diameter. If you're doing this for real, wear eye protection and keep clear of the loaded wire and the masses. Stress accounts for area, strain accounts for the original length. Their straight line ratio is the Young modulus. A steep gradient means a very stiff, but not necessarily very strong material. In the next lesson, force per unit area returns, this time as pressure. We'll be using pressure differences to explain upthrust.